Welcome to the lesson on the graphical representation of data. At the end of this lesson, you will be able to identify the purpose of representing data graphically and identify the different types of graphs that can be used to represent data. You will also be able to draw bar graphs, histograms, and frequency polygons to represent the given data. Mr. Shoestring is looking hassled. His boss wants a report of the monthly sales from last year. Mr. Shoestring has the data in a tabular format. It will take him some time to find the information asked by his boss. But his boss is in a real hurry. Let's help him with this task. You just have 10 seconds to spot the month in which maximum sales were made. Quite difficult, right? If the amount of numerical data is large, interpreting it quickly is difficult. Is there an easier and quicker way to interpret data? Yes, there is. Data can be represented as graphs for quick and easy interpretation. Look at these figures. It is the same data that Mr. Shoestring was struggling with. Identifying the month with the maximum sales can now be seen in a jiffy. Now, the figure we use to represent Mr. Shoestring's sales figures is called a bar graph. A bar graph uses bars or rectangles of the same width but different heights to represent different values of data. Let's see how a bar graph is drawn. Remember Mr. Pinch Hitter, our star batsman. He's going through a bad form. Here are the scores he made in his last 10 innings. Let's draw a bar graph to represent this data. We will use the x-axis and the y-axis to represent a variable and its different values. Here the variable is the number of innings and its value is the corresponding number of runs scored in each inning. We usually use the x-axis to represent the variable and the y-axis to represent its corresponding value. Next, we'll choose a comfortable scale to mark the data in the variables column on the x-axis. For convenience and symmetry, we mark 10 equidistant blocks to represent the 10 innings played by Mr. Pinch Hitter. Let's look at the maximum value in the values of the variable to decide on a suitable scale for the y-axis. Here the values of the variable are the runs scored and their maximum value is 49. Let's choose a scale of 1 unit equal to 5 runs and mark equidistant points on the y-axis to represent a maximum of 50 runs. Next, we'll draw bars for each innings on the x-axis representing the number of runs scored in it as per the scale chosen on y-axis. For example, in the first innings, the score was 16. So a bar corresponding to score of 16 on the y-axis is drawn. For the second innings, a bar corresponding to a score of 18 is drawn on the y-axis. Similarly, we draw the bars for the other innings. But notice that the score is 0 in the 6th and 9th innings, so no bar is drawn. This is the completed bar graph. Note that in the bar graph, the bars have equal gaps between them. The width of the bars does not matter, though we keep it constant for the sake of symmetry. The height of the bars represents the runs scored in each innings. Now, here's another collection of data. In this table, the marks obtained by 60 students in the Maths Olympiad are given. Can you recognize what kind of a table is this? This is a grouped frequency distribution table that has data grouped in continuous class intervals. How do we represent this data graphically? Let's find out. We start by drawing two axes, x and y, as we did while drawing a bar graph. We use the x-axis to represent the variable and the y-axis to represent its value. Here the variable is the marks obtained and its value is number of students. Next, we'll choose a scale to mark the class intervals in the marks column on the x-axis. Let's take 1 centimeter equal to 10 marks. Since there are 6 class intervals, we mark 6 equal lengths of 1 centimeter on the x-axis. Note that, since the class intervals are continuous, we will not leave any gap between them on the x-axis. Now, here is something interesting to note. The class intervals in the given table do not begin with 0. This is the reason we marked the class intervals slightly away from the 0 mark. To further indicate this, we make a small kink at the beginning of the x-axis. Always remember to do so when marking values on an axis that do not begin with 0. Next, we look at the maximum number of students to decide on a suitable scale for the y-axis. The maximum value is 16, so we can choose a scale of 1 centimeter is equal to 2 students and mark 10 such points on the y-axis to represent a maximum of 20 students. Next, we draw bars for each class interval on the x-axis representing the corresponding number of students indicated on the y-axis. For example, 6 students scored marks in the class interval 40.5 to 50.5. 14 students scored marks in the class interval 50.5 to 60.5 and so on. This is the completed graph. This kind of graphical representation of data is called a histogram. Note that the bars have no gaps between them. The width of the bars is proportional to the class intervals of data. Since the class intervals have the same width here, all bars have the same width. The heights of the bars represent the frequencies corresponding to the different class intervals. The area of each rectangle is also proportional to its corresponding frequency. Now the school has decided to give honor certificates to all the students who scored above 70.5 in the Maths Olympiad. To show how many students scored the required marks, the data table was modified as shown here. Let us see how a histogram representing this data looks like. You can see that the class intervals are not the same here. Whenever this happens, we need to apply a correction to the height of the rectangle of the unequal class interval. This is necessary so that the area of the rectangle and its height are still in proportion with its correct frequency. Here we have to adjust the height of a class interval with a width of 30 to other class intervals with a width of 10. The calculation is simple as shown here. Thus the height of the class interval 70.5 and above will be 9.66 and not 29. Now, let's look at another interesting way of representing data. Consider the midpoints of the upper side of all the rectangles in this histogram and join them with a line. Now consider two more class intervals just before and after the given class intervals. Note that we keep the class width constant. Now join the upper midpoint of the first rectangle to the midpoint of the new class interval marked before it. Similarly, join the upper midpoint of the last rectangle with the midpoint of the new class marked after it. What do you get? The figure we get is known as a frequency polygon, corresponding to the given data. The area of a histogram is equal to the area enclosed by its corresponding frequency polygon. Here is a table showing the charges of a courier company for packages with different weights. Let us try and draw a frequency polygon for this data. Let us try and draw the frequency polygon without drawing the corresponding histogram. For this, we have to find what we call class marks for each class interval of weight in the given table. The class mark for a class interval is half of the sum of the upper and lower class limits of the class. For example, the class mark for the class 0 to 20 is 10, and class mark for the class 20 to 40 is 30, and so on. As usual, we start by drawing the two axes, x and y. Here the variable is weight, and its value is the courier charges or rate. Now we mark the class marks found earlier along with the x-axis. Next, we mark the rates along the y-axis. Now, we plot the corresponding rate for each class mark on the figure and join these points. Does that complete our frequency polygon? Not quite. To complete the frequency polygon, we need to join it to the x-axis. For this, consider an imaginary class interval of -20 to 0 before the first class interval given in the table. Join the midpoint of this class interval, that is -10 on the x-axis, to the beginning of the frequency polygon. Now, consider class interval of 100 to 120 after the last class interval given in the table. Join the midpoint of this class interval, that is 110 on the x-axis, to the end of the frequency polygon. This completes the required frequency polygon.